Okay, so there was a question regarding the Routh Huwritz criterion and how you decode the Routh table, especially when there is a row of zeros, right? So I'm going to look at a few examples here to try and explain that one. So the first question here is example 6.4 in your textbook, where you have a closed loop system which has got that specific Routh characteristic equation s raised to 5 plus 7s raised to 4 plus 6s cubed plus 42s cubed plus 8s plus 56. So now when you form the Routh table, which is on the next page, you can give it a try. You will see that you get a row of zeros at s cubed, right? So this is where the s cubed row is the one that gives you the row of zeros, right? Now when you have a row of zeros, what you do is that you take the row above the row of zeros, in this case being s raised to 4, and then you differentiate that row with respect to s, and then you get the new coefficients for the s cube row. So in this case, s raised to 4 plus 6s squared plus 8, which is directly obtained from the coefficients here, you now differentiate it, you get 4s cubed plus 12s plus 0. And you substitute 4, 12 and 0 in this equation. Obviously they have divided it here, so you will get it as 1, 3 and 0, dividing throughout by 4. So now you complete your work, and the question can be asked in two ways. One, the comment about the stability of the system, and two, comment about the location of the poles. So if it's a stability comment, then you directly look at the number of sign changes, and then you can make a call on the stability of the system. But if it is a number of or location of poles, then it's slightly bit more challenging. So in this specific example, you will see that there are no sign changes, which means that the system is definitely not unstable. The next question is a discussion between it being stable and marginally stable. Now, a row of zeros indicates that there are poles lying on the j omega axis, and when poles lie on the j omega axis, it means that the system is marginally stable. Now remember the order. So you first need to look if the system is unstable, then look whether it's marginally stable, and then whether it is stable. So if it is not unstable, the next priority goes to check if it is marginally stable. And if it is not marginally stable, then we come and give the third priority to it being stable. So in this case, because there is a row of zeros, although there are no sign changes, the system is marginally stable. Now where do poles lie? That is the next question. So if you have a look here, they have described how you can talk about the location of poles, especially when there is a row of zeros. So when there is a row of zeros, what happens is that you have what is called symmetry, right? So you look at the point from which there is a row of zeros, or the row above the row of zeros, and then you start making the judgment. So to explain this further, let's look at this next example that they're given here. It's a quite long example, but anyway, when we start solving it, you'll see that the s cube row here is the one that is giving you the row of zeros. So what they've done is they've taken the s raised to 4 row, and they have differentiated it, and they've got the differentiated row. Now you put that back into your Routh table as they've done here, right? Now how do we interpret the Routh table? So we basically split the Routh table into two halves, right? So there is something that happens before the row of zeros and something that happens after the row of zeros. So the best way to answer this is by looking at this problem. So have a look here. They've called it the even polynomial, right, and the other, right? So why do they take it as the fourth order in this case? If you go back and have a look at the Routh table, you'll see that it is s raised to 4 row which is used for creating the new s cubed rows. That's why it is called the fourth order here, right? Yeah, fourth order. Now what they've done is, from the fourth order, from s raised to 4 below, they've had a look at what happens. And do you see that there are no sign changes? So if there is no sign changes from s raised to 4 to s raised to 0, then there are no right hand planes, which means by symmetry there should be no left hand planes. And in turn it means that all the poles will lie on the j omega axis. Now the other one, that is looking at from s raised to 8 all the way up to s raised to 4, you will see that there are two sign changes. The first one is from s raised to 7 to s raised to 6, and the next one is from s raised to 6 to s raised to 5. So there are two sign changes. So that is the next thing that they've done. So I have a look here. They will see that in the other case, that is starting from s raised to 8 to s raised to 4, you'll see that there are two right hand planes. So if there are two right hand planes, then by symmetry there should be two left hand planes, which would mean that there is nothing on the left hand plane, on the j omega axis. Then they take the total number of poles, right? So this is how you analyze and answer a question which requires the the number of the location of poles in a case where there is an entire row of zeros. So let me know if there's any questions with regards to this.